Hello everybody, it's Tarun. Welcome to your ninth tutorial in the signal system and control course. In the last tutorial we learned about properties of continuous time Fourier series representation and discrete time Fourier series representation of periodic signals and its properties. In this tutorial we learn about the frequency response of both the Fourier series representations and something about filtering or filters. Okay, so periodic signals which are represented by Fourier series and their response of LTI systems in terms of complex exponentials is called frequency response. Okay, so in continuous time case we are considering h of j omega is the uh, as minus infinity to infinity h of tau e to the power minus j omega tau d tau, and for discrete time we are considering sigma minus infinity to infinity h of n e to the power minus j omega n. This is something which comes from Fourier transforms, okay, which I'll teach you in the next unit. Okay, and in this, for this filtering or frequency response process, you just remember that h of j omega and h of e to the power j omega are these terms. You will understand them when I'll teach you Fourier transforms. Okay, so now let's see the input output relationship using the frequency response. So for continuous time case we are having input xt as summation k is equal to minus infinity to infinity ak e to the power minus ak e to the power j k omega naught t. Okay, so yt will be yt, which is the frequency response related with the input signal xt. It will be summation k equals to minus infinity to infinity ak e to the power ak into e to the power j k omega naught t will remain same, and we'll just get multiplied with h of j k omega naught, okay, which is something similar to the frequency response of complex exponentials, which I told you in the 7th tutorial where I started this unit. Okay, and for discrete time case we have xn equals to xn equals to summation k is equal to 1 over 1 time period n ak e to the power j k 2 pi by capital N into small n, and its frequency response will be this. Okay, where all the terms will remain same but it will be multiplied inside summation with h of e to the power j k 2 pi by n. Okay, so yt and yn have same fundamental period, okay, as xt and xn. Okay, and so this is the summary of this frequency response, that if x of t has sorry, not the summary, the Fourier series coefficients of the frequency response. If xt has Fourier series ak, then yt will have Fourier series ak into h of j k omega naught. Okay, and if xn is Fourier series ak, then y of n will have Fourier series ak h of e to the power j k 2 pi by n. Okay, so you can see that here the Fourier series is ak, okay, and here this is the Fourier series, and for discrete case it is Fourier series, and for yn it will be this. Okay, so the process of converting xt to yt or ak to ak into h of j k omega naught t is referred as filtering. Okay, so depending on the shape of frequency response there are some properties related to it, that filters change the shape of frequency spectrum. Okay, Fourier series coefficient of input signal. Okay, and we can pass some signal or through a filter to remove or add some desired frequencies inside the signal. Okay, so there are some frequency selective filters which are classified as low pass filters, high pass filters and band pass filters. Okay, so I'll be teaching you about low pass filters and band pass filter and high pass filters, and I'll not be able to teach band pass filters because they are pretty difficult to understand, and you will understand them more in the course principles of communication. Okay, so now let's start with some examples and then we'll go to filters. Okay, this is a differentiator circuit or is signal where yt will be dx of t over dt. Okay, and if I am considering x of t as e to the power j omega naught t, then y of t will be j omega e to the power j omega t. So the frequency response related with this differentiator circuit, where xt is e to the power j omega t, will be h of j omega will be j omega. So if I plot its magnitude spectra and phase spectra, okay, the magnitude spectra will be omega, mod omega. So you can see that it is magnitude spectra, and for angular spectra it will be pi by 2 for omega greater than 0 and minus pi by 2 for omega less than 0. Okay, so the next circuit or signal or system which I am teaching you is 2-point averager. The 2-point averager follows this equation, which is y of n equals to half x of n plus x of n minus 1. Okay, so we are calculating the impulse response related with this equation, where y of n will be replaced with h of n and x of n will be replaced with delta of n. Okay, so the frequency response related with this signal will be h of e to the power j omega is equal to summation n equals to minus infinity to infinity h of n e to the power minus j omega n. Okay, so you can see that this signal will be valid for only two values, for n equals to 0 and n equals to 1. So if I put n equals to 0, okay, then it will become h of 0 e to the power 0, which will be 1. So it will be only h of 0. H of 0 will be half. And if I am considering n equals to 1, then it will be h of 1 e to the power minus j omega, and h of 1 will be half only. Okay, with only half. Okay, so it will be 1 by 2, half will be common, and 1 plus e to the power minus j omega. And I can rewrite it in this manner. Okay, by dividing it e to the power minus j omega into e to the power minus j omega by 2 in multiplied with e to the power minus j omega by 2, and doing some operations on it. Okay, so this is the magnitude of spectra related with this function, and angular spectra related with this function, or phase spectra. So now let's see the filters. Okay, the first filter which I am going to teach you is ideal low pass filter. For continuous time case, we are considering h of j omega equals to 1 for omega less than mod omega less than equals to omega c, and it will be 0 for mod omega greater than omega c, where the omega c is called cutoff frequency. Okay, so if we are passing any signal through this low pass filter, then the input having frequency between minus omega c and omega c will be passed, and other than that will be stopped and will be made 0. Okay, and for discrete time case, it is a periodic signal, h of e to the power j omega, and no difference other than that. For now, let's see the next filter, which is ideal high pass filter. For continuous time case, it will be 0 between minus omega c and omega c, which is the cutoff frequency, and will be 1 otherwise. Okay, and for discrete time case, it is similar and periodic. Okay, and this is a band pass filter, simple band pass filter, which I am going to teach you, but the band pass filters are difficult to make, and there are very complexities in the band pass filter. So you will learn them in the POC or Principles of Communication course. For for continuous time case, what it will do, it will pass the frequencies between omega c1 and omega c2 in the both positive side and negative side. Okay, and for discrete time case, it will be followed periodically. And the last filter which I will teach you in this unit is first order RC low pass filter. Okay, you might have learned them in your high school. Okay, or in basic electronic course also. So it is also a very important circuit. Okay, the circuit is like this. There is R and C, and we are taking output across the capacitor. So the input voltage is V in and output voltage is V out. So this circuit will give us this equation, that RC d of dt V out plus V out equals to V in. Okay, and we are assuming V in equals to e to the power j omega t. Then V out will be h of j omega e to the power j omega t. So I can replace all these terms. Okay, and after replacing, I'll get the frequency response h of j omega, which is 1 upon 1 plus RC j omega. So this was all about filters and frequency response. So, and this was all in this unit. So thank you guys for watching. I'll see you in the next tutorial, where I'll start with the next unit, which is continuous time Fourier transform. Okay, so thank you guys for watching.